8.6 Nuclear reaction. Nuclear reaction is occur when an element or structure of a nuclei is bombarded by an energetic particles. When this thing occur, energy will release due to mass defect. So if you want to calculate for the energy release, we need to find the mass defect. There are two types of nuclear reaction. First, nuclear fission. Second one is nuclear fusion. From these two animations, we can see that for fission reaction, we have uranium that is bombarded with a neutron particles and then it will split to form a new element. Meanwhile, for nuclear fusion, we have deuterium and tritium, which are the isotope of hydrogen. They are going to combine together or fusion to form helium, and at the same time it will release a neutron particles and release energy. Nuclear fission. A heavy nucleus splits into smaller nuclei by bombarding it with particles such as neutron, proton, beta or alpha particles. So the smaller particles will bombard a heavy nucleus, bigger nucleus, and then it will make the nucleus splits into new element. From this reaction, the total mass of final products or the daughter nuclei is less than the original mass of the heavy nucleus, the parent. Meanwhile, for nuclear fusion, two light nuclei combine to form a heavier nucleus where the total mass of final product is less than the original mass of the two nuclei due to loss of mass defect, and energy release, or also known as thermonuclear energy. For this process, we need a high temperature. The example for nuclear fission, we have a neutron particle bombard a uranium, and then it will make the uranium become unstable, and then it will split into krypton, barium. It also will produce 3 neutron particles. At the same time, it will release the energy. So from the equation, we will see that a neutron particle plus with uranium, and then it will produce krypton plus barium plus 3 neutron particles plus with the energy. So you can calculate the total number of nucleon on the left side with the total number of the nucleon on the right side should be equal. Same goes to the proton number. Example 8.17. There are two possible ways by which uranium can undergo fission when bombarded with a slow neutron. Okay, so ada dua possibility when a uranium is bombarded with a neutron. First, dia akan menghasilkan xenon and strontium. Second possibility is it can release tin and also molybdenum. In each case, neutrons are released, so we need to write the equation for each of the nuclear reaction and determine the number of neutron released. When you write the equation, we are going to balancekan the number of nucleon and the number of proton. From there, we can see what is the number of neutrons released for these two possibilities of reaction. The first one. When uranium is bombarded with a neutron particles, it will produce xenon, strontium, neutron particles plus with energy. When you want to balance the nucleon number and proton number, we will get that there will be 2 neutron particles that will be produced. Second one, when uranium is bombarded with a neutron particle, it will release tin, molybdenum, and 3 neutron particles plus with energy. Okay, so to make the equation balance, there will be 3 neutron particles released during this reaction. So for the first equation, there will be 2 neutron particles released, and the second equation, there will be 3 neutron particles released. Example 8.18. When a uranium nucleus is bombarded by a slow-moving neutron, one possible fission reaction will produce lanthanum and bromine as products. A. Write down the equation. B. How many neutrons are released? C. Calculate the energy release. And D. What is the energy release if 10 grams of uranium is used? Okay, let's do the equation. Uranium plus with a neutron, it will produce lanthanum, bromine, and when you balance the nucleon number and proton number, we will get 3 neutron particles plus with the energy. For question B, how many neutrons are released? So from this equation, there will be 3 neutrons released. Question C, to find the energy release, we need to find the mass defect first. By using this equation, delta M equal to summation mass of before the reaction minus with summation mass after the reaction. For before the reaction, we have uranium plus with the neutron. So this is the mass. For the total mass after, we total up the mass for the lanthanum, bromine plus with 3 mass of neutron. Then we will get the delta M equal to 0.1822U, convert it into kilogram, and then substitute into the equation E equal to delta MC square. So the answer will be 2.72 times 10 to the power of negative 11 joule. So this is the energy released during the reaction, or also known as Q. For D, what is the energy released if 10 grams of uranium is used? From the equation, we only have one particle or one nucleus of uranium used in this reaction. And one nucleus or one particle of uranium will release 2.72 times 10 to the power of negative 11 joule of energy. This energy we got from question C. What if we use 10 grams of uranium? So what you need to do is, we need to find how many particles or how many nucleus inside 10 grams of uranium. So from this equation, we'll get the number of particles in 10 grams of uranium. We get 2.56 times 10 to the power of 22 particles. So we can compare if one nucleus of particles will release 2.72 times 10 to the power of negative 11 joule of energy. What if we use 2.56 times 10 to the power of 22 particles? So you just darabkan saja dengan 2.72 times 10 to the power of negative 11 joule. Then we'll get the total energy release if we use 10 grams of uranium. So here we have this ratio equation. If one nucleus or one particle of uranium release that energy, then 2.56 times 10 to the power of 22 nucleus or particle of uranium will release 6.96 times 10 to the power of 11 joule. Thus, 10 grams of uranium, it will contain 2.56 times 10 to the power of 22 nucleus, and it will release 6.96 times 10 to the power of 11 joule of energy. Example 8.19, uranium nucleus bombarded with a slow-moving neutron would produce barium, new nucleus X, and 3 neutrons. Write the equation, and if 200 mega electron volt of energy is released, determine the atomic mass for element X. Okay, so for the equation, we have a uranium plus with a neutron, it will produce barium, unknown element X, plus with 3 neutrons, and plus with energy. So for the new element X, you can balance the equation and you will get the number of nucleons and number of protons here. And then refer to the periodic table, you will see that X is also equal to the krypton. For question B, to determine the atomic mass for element X or krypton, so we are given the energy 200 mega electron volt, then substitute into the equation E equal to delta mc square. So 200 mega electron volt equal to delta mc square. So we don't have the value of delta m yet. Substitute the speed of light, you will get the delta m equal to 3.56 times 10 to the power of negative 28 kilogram. Convert into unit U, 0.2142 U. So from this value, we can find the atomic mass for element X or krypton by using this equation. Okay, you substitute delta M from the value that we get, delta M, and then substitute the mass for uranium, neutron, barium, and also 3 neutrons. So we can determine the atomic mass for element X, where we will get 91.9 U. Nuclear fusion. This is the example where deuterium and tritium will fuse or will combine together to form a helium, and then at the same time it will release one neutron and energy. This is the example of the equation. Example 8.20. A hydrogen atom undergo fusion with a deuterium atom, producing an isotope of helium atom. Write the equation, calculate the energy release, and determine the total energy release if 2.5 kg of helium is produced. So for the equation, it will be hydrogen plus with deuterium, it will produce isotope of helium. Okay, so it will be balanced. For the energy release, let's find the delta M, mass defect. So summation mass before is the summation of hydrogen plus with deuterium minus with the summation mass after, which is the isotope of helium, H32. Then we will get 0.0048 U, convert into kilogram. And then substitute the delta M into the equation, E equal to delta mc square. Then we will get 7.17 times 10 to the power of negative 13 joule. For question C, if 2.5 kg of helium is produced. So from this equation, if one particle or one nucleus of helium is produced, at the same time it will release 7.17 times 10 to the power of negative 13 joule of energy. Then if the reaction release 2.5 kg of helium, how many energy that will be released? So what we need to do is find the number of nucleus or number of particles inside 2.5 kg of helium. Okay, by using this equation, mass per molar mass times with the Avogadro constant, then we will get in 2.5 kg of helium produced, there will be 4.99 times 10 to the power of 26 particles. Then from this value, we can find the total energy release. Okay, if one nucleus of helium produced, it will release 7.17 times 10 to the power of negative 13 joule of energy. Then 4.99 times 10 to the power of 26 nucleus or particles of helium that will produce, how many joule of energy that will release? Darabkan sahaja, then we will get 3.58 times 10 to the power of 14 joule. Example 8.21. A lithium nucleus is struck by a hydrogen atom, producing a pair of alpha particles. Write the equation and calculate the energy released. For the equation, lithium plus with hydrogen atom, and then it will produce a pair of alpha particles. That means there are two alpha particles or two helium that will produce plus with the energy. For the energy released, use this equation to find the mass defect. Mass of lithium plus with mass of hydrogen minus with 2 times with the mass of helium. When you get the mass in U, convert into kilogram and then substitute into the equation of E equal to delta mc square. So the answer will be 2.78 times 10 to the power of negative 12 joule. Okay, if you want to find the energy release during the process, if the process is involving binding energy of a nucleus, then use this equation to find the mass defect. After that, substitute into the equation E equal to delta mc square. But if the equation is related to spontaneous decay or nuclear reaction, first you need to write the balance equation, then use this equation to find the mass defect. After that, substitute into equation E equal to delta mc square. So that's all for this chapter. All the best in your final exam.